In this paper, we present a framework that treats calibration not as a heuristic manual tuning, but as a unified bi-level optimization problem. Accurate estimation of the robot's base velocity and orientation is fundamental for lagged robot autonomy. To get accurate estimation, the estimator needs both well-chosen noise covariance and an accurate kinematic model. In practice, however, both are hard to obtain, and hand-tuned covariance remain common, even though they are heuristic, time-consuming, and can limit accuracy, especially under kinematic uncertainty. There are methods for noise statistics identification, but many of them are sensor-specific, make restrictive assumptions, or need careful initialization. At the same time, system identification, noise calibration, and estimator design are usually handled as separate problems. So the main gap is that we still lack a unified calibration loop that jointly optimizes these components for lagged robot state estimation and is validated across diverse lagged robots. To bridge this gap, we introduce a unified parameter vector theta as the target of calibration, which jointly capturing the covariance matrices and the kinematic offsets. Each covariance block must stay positive definite. For each lag, we calibrate a constant foot offset expressed in the calf frame. And for the torso, we calibrate a constant base offset between the mocap and the URDF torso. At the lower level, we fix the calibration parameters and solve maximum a posterior problem. Concretely, we run a optimization over the whole trajectory, seeking the trajectory that best fits the IMU-driven process model and the kinematic measurement model. In this formulation, the process and measurement residuals are weighted by the covariance, and the associated uncertainty is modeled through additive Gaussian noise with task space residual covariance obtained by analytic propagation from the raw sensor noise. With the estimated trajectory generated, the upper level evaluates the current calibration parameters by defining a geometry-aware loss that measures the deviation between the estimated and ground truth trajectories on the product manifold of the state. The upper level is solved by iterative linearization. At each iteration, we linearize the loss around the current theta, solve a constrained convex linear minimization step over the feasible set, and update. The updated parameters are then sent back to the lower level estimator, closing the calibration loop. Instead of using expensive numerical differentiation, we differentiate through the estimator analytically. Once the lower level problem is solved, its first-order optimality condition is approximately satisfied. We obtain the trajectory sensitivity by differentiating the KKT system through the implicit function theorem. With this trajectory sensitivity, we apply the chain rule to obtain the analytical upper-level gradient. This analytical gradient is then used in the iterative linearization step to update theta. We first test the method on a 5-linkage walker in MATLAB simulation, where we deliberately inject white Gaussian noise on the joint encoders, correlated non-diagonal noise on the IMU, and an articulated cuff length offset in the kinematic model. The results show that calibration converges, recovers the calf offset toward ground truth, and significantly improves velocity estimation accuracy as reflected in the much lower RMSE. We see the same pattern on Unitree Go 1 in Mujoko. Despite process and sensor noise and an injected mocap to URDF torso offset, the calibration converges, recovers the frame offset, and significantly reduces the velocity RMSE. Last and most importantly, we validate the method on real Unitree B1 hardware. The robot walks in a motion capture room where the torso motion is measured as ground truth. After joint calibration, the estimated trajectory aligns closely with the ground truth, with a clear reduction in RMSE across the evaluated states. To close, the key message is that we jointly calibrate noise and kinematics through a unified bi-level optimization framework, and this significantly improves state estimation. Looking ahead, we want to better understand observability, extend the framework to more general robotic systems and sensing modalities, and develop faster solvers by exploiting the problem structure more fully.